The Unit 4 of this course has been divided into two parts, gas chromatography and liquid chromatography, attending to the physical state of the mobile phase. In this first part, 4.1, we will deepen the gas chromatography. First, some theoretical fundamentals. Then, we will review the components of a gas chromatograph. Gas chromatography is an instrumental separation technique employed in all analytical laboratories. It's mainly used for the separation of volatile and thermostable substances. This is substances that don't degrade by heating. A large number of organic and organometallic compounds, as well as permanent gases, are involved. Then, it's not suitable for thermally labile compounds. In gas chromatography, the mobile phase is a gas, also called carrier gas, and the stationary phase can be a solid sorbent. This modality is also called gas-solid chromatography, or it can be a low volatile liquid film coating, an inner solid support, or the column tube wall itself. This second mode is also called gas-liquid chromatography. In gas-solid chromatography, the main separation mechanisms are: first, due to the equilibrium caused by adsorption and desorption on the surface of the particles that form the solid support, and second, due to the differences in volatility of the solutes. The materials most commonly employed as stationary phases in this kind of chromatography are silica gel, alumina, activated carbon, and zeolites. So, attending the stationary phase polarity in this chromatography is mainly normal phase chromatography. Their current applications can be summarized as the separation of permanent gases, for example, carbon dioxide, oxygen, ozone, nitrogen oxides, and low boiling point compounds, such as formaldehyde, methanol, etc. In gas-liquid chromatography, separation depends on, first, the solubility of the solutes in the stationary phase. The higher the solubility of a constituent, the slower it moves through the column, so the higher the retention time. And second, the volatility. The more volatile the substance, the faster it moves through the system. This gas chromatography modality is generally reverse phase chromatography, and it's the one employed for a greater number of practical applications. We will refer to this topic later on. A gas chromatograph is the instrument whose main functions is to provide the necessary conditions for the separation of the components of a mixture. Let's go now to review the different parts of such instrument. First, a carrier gas or mobile phase supply and inlet. B, an injection port to introduce samples and standards. C, a chromatographic column. D, a thermostatized oven. E, a detection system to generate the required information. And finally, a data recording and treatment system. A general description of the process is indicated by the arrows in the slide. The sample is injected through a rubber septum into a hot injector, coated with glass or metal, where the sample is vaporized. The sample is pushed by a carrier gas stream into the column, which is inserted in an oven. By a rise in the temperature, the sample components are separated and finally reach the detector, where the signal is recorded as a chromatogram. The column temperature doesn't need to be higher than the boiling point of all solutes. It just needs to be high enough so that each solute has sufficient vapor pressure to be eluted in a reasonable time. The detector, on the other hand, is kept at a higher temperature than the column, to remove all the solutes coming from the column and prevent contamination by further condensation. Let's look at them in more detail. Mobile phase delivery. The mobile phase is a gas with the only function to carry all components to the stationary phase. This means that it doesn't play any role in the separation process. For such a reason, it's also called carrier gas. The most commonly employed gases are helium and nitrogen, but also argon, hydrogen, and carbon dioxide can be used. The requirements are that it must be a pure and inert gas with little or no solubility in the stationary phase, and that it must be compatible with the detector, meaning that it must not give any response. The choice of the carrier gas will therefore depend on the nature of the sample, the detector, and the stationary phase. Cost can sometimes also make the decision between, for example, helium and argon. Helium is more expensive than argon. In any case, it's always very important that it's free from impurities. Typical impurities are water or oxygen, which may hydrolyze or oxidize respectively the stationary phase, and are incompatible with some detectors like electron capture detectors. Other impurities can be light hydrocarbons that produce noise in flame detectors. All these things will be reviewed later on when we talk about detectors. The flow or speed of the mobile phase directly influences the efficiency of the separation, as we have already studied the Van Ginter equation. Remember, this equation expresses the theoretical plate height as a function of the velocity of the mobile phase in a column chromatographic system. Then, there is an optimum flow rate for each column when it reaches the minimum value for plate height. Observing the Van Ginter plot, there are two different slopes. Being higher, the slope to the left of the minimum H value, than the slope to the right. Therefore, it's better to work at flows higher than the value predicted by the equation rather than below, because efficiency will be less affected. The velocity of the mobile phase also depends on the nature of the gas, mainly its viscosity. Thus, hydrogen is, of the three commonly employed gases, the one that allows faster separations under equal conditions, by giving more flexibility in terms of flow rate. It should be noted that the viscosity of these gases increases with temperature, so this is another important parameter for increasing efficiency. For example, at the same temperature, helium is more viscous than hydrogen, so it's more convenient to work with hydrogen if possible. The carrier flow rate is controlled by pressure gauges. High pressure gauge is required in order to control the gas flow rate connected to the outlet of the compressed gas. Low pressure gauge will provide gas to the flow controller and the flow meter connected to the column. Within the flow meters, the most common are bubble and electronic. There are also several possibilities for flow controllers: mechanical, needle, electronic, and mass flow. There is also need to place some traps for potential gas impurities removal. The injection stage in gas chromatography is critical, especially for quantification. Two aspects of the injection must be distinguished. On the one hand, the device used to take the sample is usually a microsyringe due to the small volumes injected. The syringe consists of a calibrated gas cylinder in which a plunger is inserted that can be operated manually or automatically. The volume of sample to be injected depends on the type of colon and the physical state of the sample. The samples to be analyzed can be liquids, gases, but once they enter the injector, they have to be in vapor phase. Typical injection volumes, depending on the type of colon and physical state of the sample, are shown in the slide. Packed colons with higher internal diameters accept higher volumes than capillary columns. Likewise, the volume of gas samples can be higher than liquid samples. A poor injection technique can decrease peak resolution and then the results quality. It's quite obvious that wherever technique is used for sample injection, the primary objective is to produce a narrow band at the head of the colon, containing a representative composition of the original mixture. The bands, as they advance through the colon, will widen, so they will never be narrower than at colon head when they enter the colon. That means that the injection should be as fast as possible to avoid this band broadening affecting the resolution. Then, the hotter the injector gate, the better the injection. Also, the amount of sample injected must be adjusted to the colon capacity to avoid stationary phase overloading, as this affects the colon resolution capability. In addition, the carrier gas flows into the injection system and pulls the vaporized sample into the colon. To avoid band broadening, the dead volumes around the injection area and the colon must be kept to a minimum. At the end, as one of the major sources of gas chromatography errors are due to injection-related problems, they are usually corrected by calibration with internal standards. We will return to this aspect. The second basic component for a correct injection is the injection port installed. As we previously said in gas chromatography, all the components entering the colon must be in the vapor phase. The design of the injector is critical to obtain good quantitative results in the analysis. With on-colon injection, a liquid sample is directly introduced into the colon with a thin injection needle. During the course of the temperature program, the vapor pressure of the solutes increases and the chromatographic process begins. By using an initial temperature below the boiling point of the solvent, selective evaporation and hence discrimination is precluded. This is why on-colon injection is often chosen for samples containing high boiling components that wouldn't be quantitatively transferred to the colon in other injection modes. It's clear that with this injection mode, small sample amount is injected. This on-colon injection is shown in 3 steps on the slide. With the aid of the microsyringe, a sample amount is injected through a silicone septum directly into the injector port where the colon head is located. The injector temperature provided by the metal injector block must be sufficiently high for the sample to volatilize completely without decomposition. This is called flash vaporization. As a general rule, the injector temperature is about 50 degrees higher than the boiling point of the least volatile component of the sample. In addition, this type of injection requires a valve system that prevents the carrier gas from passing through the colon while injecting, represented in stages 1 and 2 of the slide. And when the sample is deposited and the needle comes out, the valve opens and the carrier gas passes through again, represented by stage 3. Capillary columns are generally employed in gas chromatography as they provide a high number of plates, being more efficient. Small flow rates must be used with sample volumes between 0.1 to 3 microliters to be injected. For narrower capillary columns, known as narrow bore, it's advisable to inject 50 nanograms or less, while for large capillary columns, also called wide bore, up to 100 to 200 nanograms of compound can be injected without saturating the column. We will return to this point. As this small flow rate is difficult to control, the on-column injection is not the best option. Therefore, injectors of a different type must be devised. The splitless injector, meaning with or without flow division, is the mostly chosen one. This injector consists of a vaporization chamber containing a glass tube inside the injection port called glass liner, into which the sample is injected through the septum. The carrier gas reaches the vaporization chamber, where it's mixed with the injected sample as shown in the figure. A variable vent valve, usually set between 50 and 100 microliters per minute, divides this flow into two unequal fractions. The larger flows out the injection chamber, dragging most of the introduced sample. Consequently, only a fraction between 1 and 10% of the sample volume is addressed to the column, depending on the diameter of the capillary column used for the separation. Such a sample fraction in jet can be expressed by the ratio of those two flows as expressed in the equation of the slide. Although the flow splitting injector avoids, in part, the overloading of the column, it has some drawbacks. First, lower sensitivity, because a good part of the sample is disregarded. This fact is particularly important in trace analysis. Second, the difficulty to reproduce split radio adjustment leading to poor reproducibility. And third, when the sample contains components with very different volatilities, is rarely uniform and the injective fraction is enriched in the less volatile components. Apart from those two direct injection systems, there are other injection options in gas chromatography. One widely used is thermal desorption. As shown in the slide, it consists of an oven where the sample is desorbed from a vial or a column at a chosen temperature under a stream of carrier gas. As the components vaporize, they are retained in a cold trap, usually cryogenic trap supported with liquid nitrogen, until completion of the desorption process. At this point, injection is carried out by very rapid heating of the cold trap, and the vapors generated are directly transported to the head of the column. This kind of injection is generally employed when a preconcentration factor is advisable for detection of small analytes concentration. The third modality for gas chromatography sample injections is known as headspace. It's generally applied for highly volatile compounds. It consists of analyzing an aliquot of the air in contact with the sample in order to determine the vaporized fraction of the components in equilibrium with the liquid sample. For this purpose, the sample is introduced into a sealed vial and subject to the appropriate temperature during the necessary time to reach the equilibrium between the liquid and vapor phases. The figure in the slide shows three injection possibilities when employing this technique. The static headspace, A fixed time of equilibration is applied and the estimated amount is sampled with the syringe and injected into the gas chromatograph. The main problem of this modality is the lack of reproducibility, and as it's sometimes difficult to know when equilibration is fully established. The dynamic headspace, there is no equilibration time. As soon as the components vaporize, they are cold-trapped. After a certain time, the sampling is finished and the amount collected in the trap is desorbed. And dragging and trapping. This is a variation of the previous one. Now the carrier gas bubbles through the liquid phase, dragging the volatile components from the liquid phase core. The column is the core of the gas chromatograph. Keep in mind that the column, where the stationary phase is contained, is the real element of sample components separation. Thus, a bad choice of the column or inadequate working conditions according to column specifications will never allow good results. These reasons account for the vast majority of problems encountered when performing a gas chromatographic analysis. The characteristics of an ideal gas chromatography column are wide operating temperature range, leading to greater experimental conditions flexibility. Some columns can go up to 500 degrees. Good chemical and thermal stability to prevent reactivity with the sample components, getting longer column durability. Low viscosity that offers less resistance to analyte transfer between phases, thus making the column more efficient. High purity of materials, assuring high selectivity and reproducibility, and minimizing the possible presence of ghost peaks. Good adherence to the stationary phase to support, preventing bleeding effects. The stationary phase plays a fundamental role for gas chromatography, since the mobile phase is inert, and the separation are exclusively due to the specific interactions that occur between the sample components and the stationary phase. In the introduction of this unit, it was said that solid stationary phases are made up of various adsorbent materials, such as deactivated silica or alumina, mineral salts, molecular sieves, glasses or porous polymers, etc. They are used only to separate permanent gases or low molecular weight hydrocarbons. Actually, most stationary phases in gas chromatography are liquids that are deposited in a solid support, which can be the column tube itself or another inner support covering the column walls. Some widely employed compounds are methyl polysiloxanes, polyethylene glycols, etc. Concerning column geometry, there are two main types of columns in gas chromatography. Packed columns, usually made of stainless steel or glass, and normally have an internal diameter between 3 and 6 millimeters and a length of 1 to 3 meters. There are two components, solid support and stationary phase. The solid support must have a number of characteristics, which are a high surface area to ensure a thin and homogeneous stationary phase film distribution in order to provide the maximum contact with the analytes for mass transfer. A high porosity and thermal stability due to the same reasons explained with stationary phases. To be hard to prevent the particles from fragmenting during the impregnation of the stationary phase, and to be totally inert to prevent undesirable reinteraction with the stationary phase and/or the sample components. Among the most employed are the diatomaceous earths, fossil and microscopic algae skeletons, silica or metal oxides, which are previously treated to reduce surface activity and make it more inert. Other supports are commercial, like chromosorb, nichrome, etc. The filling is confined inside the tube by means of plugs of some porous materials, generally glass wool or quartz wool, located at the ends. The stationary phase can be a solid. In such a case, the column is filled in with particles, or can be a liquid deposited to the support. For liquid stationary phases, the percentage loaded is a key parameter that must be strictly controlled. If the amount is too low, the support surface could be exposed to the sample, being absorbed and resulting in wider peaks. On the contrary, if the loading is excessive, retention of the compounds can increase too much. The usual loading percentage is from 2 to 10%. The diameter and uniformity of the particles of the stationary phase also influences the efficiency of the column. The smaller and well distributed, the better the efficiency. The second type of chromatography columns for gas chromatography are open capillary columns. These columns have smaller internal diameter between 0.1 and 0.5 millimeters. Then they can be much longer than packed columns, 20, 50, even 100 meters. These two characteristics make these columns more efficient than packed ones. Silica is the material mostly employed to prepare the capillary, playing the role of solid support. The stationary phase in these columns is always a liquid deposited into the silica capillary tube. The most currently employed are methyl polysiloxanes with low polarity, polyethylene glycols low moderate polarity, or polyesters moderate high polarity. Often, to minimize losses of liquid stationary phase by volatilization, cross-linked immobilization, or chemically bound to the support strategies are applied for the liquid film stationary phase coating. Within the capillary columns most commonly used today, there are two main types depending on how the stationary phase is immobilized into the capillary. Wall-coated open tubular. These are open tubular columns with coated walls where the liquid stationary phase is spread directly onto the inner wall of the capillary tube. These are the most efficient as the column is empty, and therefore all the diffusion and channel formation problems predicted by Van Deemter don't occur now. Support-coated open tubular. Columns in which the wall has been coated with a mixture of finely divided microparticles, usually silica gel or alumina, and a known amount of a liquid phase. Porous layer open tubular. Columns in which the wall has been coated with a thin layer of porous polymer that has been considerably extended by macroparticle deposits. Comparing WV-cut and Scott-plot columns, WV-cut are more efficient as they are empty, and Scott-plot columns have greater capacity. Among the parameters that control the efficiency of a capillary column are the length, the internal diameter, the stationary phase thickness, and the stationary phase particles. Concerning the column length, in the efficiency and the resolution of a complex mixture, it's shown in the two chromatograms of the slide. Both have been obtained under identical experimental conditions, except for the column length. One is twice as long as the other. It can be noticed that the longer column gives better separation of the mixture components. Regarding the stationary phase thickness, the thinner the stationary phase layer, the more efficient, but the compound's selectivity decreases under these conditions. On the other hand, the thicker the stationary phase, the higher the retention and selectivity. But as retention time increases, the peak with 2. Typically, films between 0.1 to 3.0 microns are used as a compromise of both situations. Another parameter that will greatly increase efficiency is the particle size. Smaller the size, higher the efficiency. The reason for that is they offer less resistance to the flow of components, and therefore it will be possible to increase the flow velocity and greatly lengthen the column. Table of the slide summarizes the characteristics of packed columns instead of capillary columns. The great use of capillary tubular columns is mainly due to their high efficiency, highlighted in green, 30,000 to 50,000 plates compared to 2,000 to 4,000 of a packed column. On the other hand, the high efficiency of this type of columns allows good resolution to be achieved without resorting to highly selective stationary phases. The main drawback of capillary columns, however, is their small loading capacity, orange row, requiring special injection systems to introduce small amounts of sample and detectors with high sensitivity. Then, these columns have a very high potential use in the field of trace analysis. The selectivity of the stationary phase depends on the different intermolecular forces established between solutes and stationary phase. There are different forces. First, London dispersion forces for nonpolar solutes, the Debye induction forces for polarizable solutes, the Kizom orientation forces for moderate polar solutes. These three are van der Waals intermolecular forces. And 4, the donor-acceptor bonds, like hydrogen bond for polar solutes. When separating nonpolar compounds, the only interaction between the solutes and the stationary phase are dispersion forces solutes. So, the solutes emerge from the column in order corresponding to their boiling points. If there are more polar compounds in the mixture, the most important interactions are due to induction and orientation forces, and in some cases to donor-acceptor bonds. The sum of all the interactions between the solutes and the stationary phase is a measure of the polarity and marks the general retention characteristics leading to better selectivity. The effect of polarity and volatility of the compounds are the responsible of their elution order. We will present in the next slides some of the most used solid and liquid stationary phases for gas chromatography. In gas-solid chromatography, silica gel, alumina, graphite, and molecular sieves, zeolites, are generally employed. Another group of adsorbents is formed by porous organic polymers. There are several types of commercial polymers that have sponge-like structures where the solvent fills the pores, and after evaporating, the polymers stays in the pores. The main disadvantage of this type of adsorbents is their relatively low maximum working temperatures and high bleeding, hindering their use with sensitive detectors. In gas-liquid chromatography, two main adsorbents are employed as nonpolar or moderate polar stationary phases, squalene and polysiloxanes. Polysiloxanes or silicones are by far the most widely used group of stationary phases due to their high thermal stability and the possibility of chemically modifying the base structure to obtain phases with different polarity and selectivity. Another important group is polyethylene glycols for separation of more polar compounds. Polysiloxanes are based on the general structure represented in the slide, where R can correspond to methyl, vinyl, phenyl groups. The whole structure can be substituted by a single group or by mixtures. The great possibilities of structural variation of these compounds make possible to obtain highly selective stationary phases. Polyethylene glycols are prepared by polymerization of ethylene oxide, which gives rise to the structure in the slide. The fundamental factor that marks the retention characteristics of this type of stationary phases is the concentration of hydroxyl groups, and to a much less extent the average molecular weight of the phase. This latter factor, on the other hand, has a great influence on the thermal stability of the phase. As an example, Carbowas 20M with an average molecular weight of 14,000 has a maximum use temperature of 225 Celsius degrees, while Superox 4 with an average molecular weight of 4 million is usable at temperatures up to 300 Celsius degrees. To end with stationary phases in gas chromatography, we must say that one of the factors influencing the upper limit temperature of the stationary phase is the tendency to be entrained by the carrier gas stream as the viscosity of the phase decreases with temperature. This effect is particularly important in the case of capillary columns. A solution to this problem consists of chemical immobilization of the stationary phase, either by chemical anchoring the liquid phase on the surface of the capillary or by chemical cross-linking the stationary phase molecules to form a three-dimensional reticulum of low mobility. These stationary phases are known as bound phases or immobilized phases, and offer higher working temperatures than conventional ones. Moreover, since phases of this type are practically insoluble, a large volume of solvent can be injected.